This is Brenda Wingard-Haynes, and we are at Biochem 208, and this is the second segment that we're going to look at on enzymes and vitamins. In the last segment, we talked about the fact that even though we have a relationship called Gibbs free energy of delta G equals delta H minus T delta S, we are going to ignore this part right here because temperature and entropy will be such a small component that basically when we talk about reactions going forward, we're going to use delta G and delta H interchangeably. The upshot of it here is that we can look at energy graphs such as these two that I put on your notes, and we can actually calculate the actual value of the activation energy and the enthalpy of reaction. This one on the left is negative, so this one would be exothermic, and it would just go faster with an enzyme. This one on the right is endothermic, it's positive, and it is not favorable even with an enzyme. So what we want to do is we want to couple reactions together. So there's a couple of examples here. ATP yields ADP plus inorganic phosphate plus 7.3 kcals per mole. 7.3 kcals per mole is produced, so its enthalpy is negative. Now I can couple it with an arrow like this, or if you don't like that, I can just draw a straight arrow. Either way. My second reaction is pyruvate to oxaloacetate, and because I put the energy here on the left-hand side, that means that energy has to be put into it. So pyruvate to oxaloacetate has energy put into it, which makes its enthalpy positive. It is endothermic. So on its own, this reaction would go forward and yield 7.3 kcals per mole. Well, we don't want to waste that 7.3 kcals per mole, so we're going to use this 7.3 kcals per mole to produce the 5.6 that pyruvate needs. So we're going to add these together, and we see that we have a negative 1.7 kcals per mole overall. And so the question then says, is the reaction coupling favorable? Well, it would be yes, because delta H is equal to negative 1.7 kcals per mole, and the negative is favorable. Okay? Well, let's go the opposite direction, and let's take this reaction and go backwards, which means we have to put the 7.3 kcals per mole back into it. It's a reactant. It's on the left-hand side, so our delta H is positive 7.3 kcals per mole. This time now, instead of linking it to pyruvate and oxaloacetate, I'm going to link it to phosphoenol pyruvate to pyruvate. And instead of the curved arrow that I used up here, I'm just going to use this arrow. I'm going to add these two together. This one produces 15.2 kcals per mole, which means that my delta H over here is negative. So in other words, this one's going to liberate 15.2 kcals per mole, and I don't want to waste it. So I'm going to use that 15.2 to contribute to the 7.3 kcals per mole that's needed over here. When I add them together, I get negative 7.9 kcals per mole. So since the overall is negative, is the reaction coupling favorable? Yes, because delta H overall equals negative 7.9 kcals per mole. Okay, so coupled reactions, we're going to look at these very carefully when we get into metabolism. There will be so many of them, it will be mind-boggling. But in general, they're going to look like this. A yields B, and it will be coupled to C plus D. And the reason that they will be coupled is that there's going to be an energy requirement. So for example, I can generate heat over here, and this same heat that I generate will be used to drive this one over here. Or vice versa. This one would require heat, which means this one's going to yield heat. There's also a second reason why reactions are coupled, and that is redox. So we could end up, for example, with E goes to F, G goes to H, and for example, this one might be oxidized because this electron is lost, which means this electron that is lost has to be gained over here. So what we're going to be looking for in metabolism is overall reaction coupling and try to figure out why they are coupled. Is it a heat component? Is there a heat requirement? Or is there a redox requirement? Okay. Again, why would reactions have to be coupled because of redox? Well, you can't just have this electron being lost. It has to be coupled. All right. So the next thing we're going to do is we want to focus on these enzymes, and we're going to have to name them. And the naming is reasonably easy because almost all of them end in ASE. A few of them end in IN. Okay, so sucrase, lipase, oxidase, carboxypeptidase, acetylcholinesterase, adenylate cyclase. There are tons of them. And there are a few that end in N, renin, pepsin, trypsin. Okay, now the name gives you a clue about the substrate. And the substrate is that which the enzyme is acting on. So sucrase, the substrate of sucrase is sucrose. The substrate of lipase is lipid. Oxidases will oxidize, and so forth. Now, there are a bunch of enzymes, and while they're all important, what I wanted to do was focus on a few categories. All right? Now, dehydrogenases will remove hydrogens. Dehydrogenases removes hydrogens, and in the process, we call those oxidoreductases. And so what that means is whenever you see a dehydrogenase, you know you're undergoing redox. And you're going to be going from a carbon-carbon single bond to a carbon-carbon double bond. Kinases. Kinases are what we call transferases that transfer phosphate. And we're going to need phosphate ad nauseum for a variety of reasons, including the fact that we want to make ATP. Isomerases are very straightforward. Isomerases are those which convert cis to trans or other rearrangements to form isomers. Carboxylases are what we call ligases. Ligases are things that add. Okay, so ligase means to add. Okay, the prefix lig, ligand, ligature, ligament means to add. So carboxylases are ligases which add carbons in the form of CO2. And decarboxylases are lysases. Lys means to take apart. Hydrolysis, lysis, lysosome. Okay, so lys means to remove or take apart. So a decarboxylase is something which removes a CO2. And if you think about it, at the very least, if we breathe in oxygen, we breathe out CO2, you know that you're going to be having shuffling of carbons and removing CO2 from the body at the very least. So these enzymes are the enzymes as a class that we will focus on.